In this video, we're going to look at using our exponential functions and some of our logarithmic properties to solve exponential functions in context. So we're going to look at doing some word problems. And our common formulas that we have to work with usually are your compound interest formula and your continuously compounding formula, which is the continuously compounding is PERT, and the compound interest, when I know the number of times something is compounding, is A equals P times 1 plus R over N to the NT power. Now, there's also another one that we could encounter, which would be Y equals A times B to the X, our standard exponential function, where if, depending on what we're given, if we're given a rate of growth where B would be equal to 1 plus or minus R, depending if it's growing or decaying, we might see one of those in this video as well. So let's look here at this first one. Sam invests $500 in an account with a 5% interest rate. How much will Sam have in 10 years if the account is compounded? And then I give you the number of times everything's compounded. So for this problem, we're going to be using our compound interest formula. The number of times compounded is n. So and so I change up the number of times it's compounded in each case. We have a 5% interest rate, so R is going to be 0.05. The amount of money that you put into the account to start with is P. So my initial amount, my principal, 500. And the number of years in this case is going to be T. So T is going to be equal to 10 years. And we need to go through first, and we need to figure out what we're going to use for N when we know how many times it's compounded. So my units of time are in years. So if I compound quarterly, how many times that happened in 1 year? That happens 4. Weekly, in 1 year, that'd be 52 times. And then hourly, I need to know how many hours are in a year. And the number of hours in a year, well, there's 24 hours in a day, and there's 365 days in a year. 365 days in a year, so I'd have to multiply 24 times 365, and that gives us 8760. So N in this case would be 8,760. Now to do these problems, we would need a calculator, and I'm going to save the compounded continuously for last. So quarterly, we're going to plug in, so the amount of money Sam's going to have if it's compounded quarterly would be equal to 500 times 1 plus R, 0.05, over N raised to the N times T power, so 4 times 10 power. And we'd get that one, and then we have weekly, so same thing, but N is 52. And then hourly, do it again, where N is 8,760. And then we would use a calculator to solve this. Now, I'm going to use Desmos to get these values. And so what we have is, we go into Desmos. Make this thing a little bigger. All right, and so we go ahead and pre-type in our equation. We don't know what n is. All right, and so I actually need to change that from a 5 to a 10. So I have my function defined with n still in it, and everything else is where it goes. And so what I would do here, because I got a few of these that we have to solve for, is I'm going to just make it into a table, and then I'm just going to type in numbers for n. So I start typing in for n. Let me change the screen so it's a little easier to see. Put in 4. So if we compound it 4 times over 10 years, the $500 becomes $821.81. If I compound it weekly at 52, it becomes $824.16. And then hourly, it's going to become, let's see, 8760. So $824.36. Now, we would expect that as we continue to increase the number of times something is compounded for the money to grow, and it will be the case, but eventually we'll get to the point where we're compounding so many times that you won't see that large of an increase as we go on. Now, if we compound continuously, it means we got to use PERT. All right, so my compound continuously formula would be the amount of money would be 500 times e to the 0.05 times t power. So it would be 500 times e to the 0.05 times 10. And to get that with Desmos, we'd have to type in a new equation. So I just typed that straight in. Desmos can evaluate that for me. And we get a value of, so it's $500 with growth. It's continuously compounded to $824.36. And you might be saying, well, wait a minute, that's the same as what we had before. It's the same because I rounded to the nearest cent. The decimal value is not the same. And so that takes us to, well, how would we define what E actually is by using this process? And so the way we would do this is, notice the part that changed the whole time when what we were doing. We basically were just using the part that was different was the 1 plus r over n to the n power. Because in my two equations, I still had t, okay? And basically the e to the r in this case is the part that I'm looking at for the 1 plus r over n to the nt power. So that's going to be equal to e to the r. Now, and not necessarily equal to, but it's the part that we're trying to figure out how would we define e. So if I let r equal 1, we're basically comparing e. We're comparing e to the 1 and 1 plus 1 over n to the n power. Well, we noticed as we started doing this problem, as we increase the number of times something is compounded, so I went from 52 to 8,760, what's happening is the value is starting to get very close to the value if I had a base of e. So I could take that 1 plus 1 over n to the n power, and basically through this process, if we're compounding continuously, we're going to apply our compounding an infinite number of times. So we'll say this is the limit as n approaches infinity will make e. Now, to show you this, what we have is I just graphed what we have inside the limit, because in Desmos I can't use limit notation. So I'm graphing the equation 1 plus 1 over x to the x power. And I graphed the line y equals e. What you're going to see, and so the limit as n approaches infinity basically means as your x values start to increase without bound. So as I start to zoom out and I look, you're going to see that the two lines become identical. That we really don't see a big difference between the two functions themselves. So as I increase the size of n, that function 1 plus 1 over n to the n power is going to converge to what e is. So that's one way to define e. There's a second way to define e if you were to Google and try to look up the definition of e. And that's going to be, instead of writing this as n approaches infinity, it's based on the fact of what is happening to the size of 1 over n as n increases without bound. Well, 1 over n as n increases without bound is approaching 0. So what I'm going to do is I'm going to write my limit a little bit differently. So I'm going to let x equal 1 over n. So basically, as 1 over n approaches 0, x is going to be approaching 0. And so our limit here would be the limit as x approaches 0 of 1 plus x raised to the, well, we have x being representing 1 over n, and we need to have an exponent of n. So if I rearrange my terms, n is equal to 1 over x. And so I put 1 over x as the exponent. That is a alternate way to define e as well. So we have two ways to define what e is. Okay, next application here. So George has an account that compounds continuously. If the account has a 5% interest rate, how long will it take his investment to triple? Now, so the fact that we're compounding continuously means that we're going to use PERT. So we got A equals P times E to the RT power. Well, the interest rate of 5% means R is 0.05. We don't know what T is, and we also don't know what his initial amount is. So, but what we do know is we need his investment to triple. So I'm going to let P equal 1, just to keep this equation as simplified as possible. And I'm going to set the equation equal to triple that value, so I'm going to let A equal 3. So the P times 3 makes 3. And so our equation that we have to solve is 3 equals 1 times E to the 0.05 times T power. So basically we have 3 equals E to the 0.05 T. And we want to solve that. So to solve that, what I would do is take the natural log of both sides. So I have the ln of 3 is equal to the natural log of E to the 0.05 times T power. Well, properties of exponents say that you can take the exponent inside the log and write it out front. And so we do that, we'd have the ln of 3 is equal to 0.5 t times the natural log of e. Well, the ln of e is just 1. So to solve for t, all I would need to do would be to divide by 0.5, which would basically be the same thing as multiplying by 2. So t would equal 2 times the ln of 3. And we would just go get that decimal value using a calculator. And we get approximately 2.197 years. Now let's look at part B. So if his deposit of $1,000 increased to $2,850 in 12 years, what was his interest rate? So we would plug in, we're still using our PERT formula, A equals P times E to the RT. We don't know the interest rate this time, but we do know that we have 2,850 equals 1,000 times E to the R times 12 power. And I want to solve. So I would solve this. I would divide by 1,000 first. So I'd have 2,850 divided by 1,000 equals E to the 12R power. And then we would take the natural log of both sides, so that way I can get what I'm solving for out of the exponents. So I'd have the ln of 2,850 divided by 1,000 is equal to the ln of E to the 12R. And then properties of exponent says that the 12R can come out in front of the ln. So we'd have the ln of 2,850 divided by 1,000 is equal to 12R times the ln of E. Well, the ln of E is 1. So all I would need to do is divide by 12. And so our interest rate here would be whatever the natural log of 2,850 divided by 1,000 is, divided by 12. And we get R to be equal to 0.0873. Now rates are commonly referred to as percentages, so that'd be 8.73% approximately. So since the half-life means that the element is constantly decaying, the most accurate way to solve these problems is going to be to use PERT. A equals P times E to the RT, because it's constantly, continuously decaying over time. Now, what we actually need to do for this is we need to solve for R in order to figure anything out. So I know that the half-life, it took 5,730 years. So what I'm going to do, even before I read question A, is I need to solve for R. So what I'm going to do is I'm going to let A be 1/2. Or actually, yeah, let's pick a different number. Let's let A be 1/2. And which means I started with 1 for P. So because half of what I started with for my half-life. And that gives me E to the R times the number of years it took to get a half of what I started with, 5,730. Now we solve this like what we were doing before. So take the ln of both sides. So I'd have the ln of 1/2 is equal to the ln of E to the 5,730R. And bring my exponents out front. So the ln of 1/2 is equal to 5,730R times the natural log of E. Well, the ln of E is 1. And then we would divide by 5,730. So R is equal to the ln of 1/2 divided by 5,730. We'll get a decimal value so that way we can actually solve for something. And so we get r to be negative 0.00012 roughly, and then that's as far as I'm going to write that decimal. That way I get a couple of significant figures to use. And now we can actually use our equation to solve these problems. So basically we have an expression representing the half-life of carbon-14 to be A equals P times E to the negative 0.00012 times T power. All right, so we did all that so we could get that in one equation. Now we're looking for part A. So part A, we have a fossil was found to have 10 grams of carbon-14 when it originally had 17 grams. How old is it? So it had 10 grams, so 10 is A. We originally had 17, so 10 equals 17. And then I write the rest of my equation, so it would be E to negative 0.00012 T power. Divide by 17, so we have 10 over 17 equals E to the negative 0.12312 T power. I take the ln of both sides from here. So we'd have the ln of 10 over 17 is equal to the ln of E to the negative 0.3012 T power. Bring the exponents out front using our properties of logs. So we'd have the natural log of 10 over 17 is equal to negative 0.00012 T times the natural log of E. ln of E is 1. And so T, in this case, what we're looking for is going to be the most accurate answer would be the ln of 10 over 17 divided by negative 0.00012, and we would get that approximate time frame using a calculator. And so we do that, and we get that this, it's taken approximately 4,421.902 years. All right, part B, a fossil is found to have 28% of the amount of carbon-14 found in a living organism. How old is this thing? So what we can do is we can let the initial amount be 1, and the amount is 28% of 1, which would be 0.28. And so we kind of repeat our process. And we're going to use our same formula that we derived for our PERT. So we'd say 0.28 is equal to E to the negative 0.00012 T power. And we solve for T just like what we just did. And so using our same process, we take the ln of both sides. So the ln of 0.28 is equal to the ln of E to the negative 0.00012 T power. Bring our exponents out front. So we'd have the ln of 0.28 is equal to negative 0.00012 T times the ln of E. The ln of E is 1, so I'm just going to cross that out. And I divide by that decimal. So the number of years for how old this thing is would be the ln of 0.28 divided by negative 0.00012. And we get the approximate number of years using our calculator. And you get about 10,608.047 years. All right, last one here for this half-life problem. We have a 2,000-year-old fossil that has 2.5 grams of carbon-14. How much did it originally have? So we're still using our derived PERT formula, so 2.5 equals P, that's what we want, the original amount, times E. Now we have negative point, we're still using that same formula we derived, so 0.00012 times 2,000 power. And then we would solve for P. So I would take leave 2.5 equals P, and then I'm going to take E and I'm going to raise it to that exponent power, and then I would divide. And so when I take E and apply that exponent to it, we get approximately 0.787, and so we would just divide 2.5 by 0.787, we get an approximate value. and we get approximately 3.177 grams. Okay, last one, let's look at a population problem. So in the year 2005, the population of City A was 150,000 people. Relative growth rate, 6% per year. Population of a neighboring city had a population of 200,000 people, relative growth rate of 3% per year. And they want me to figure some information out. Well, we're going to use PERT because there's not a defined number of times to say that the population is, the rate is compounding at. And also, if you see relative growth rate, that's also an indicator. The word relative means that we're going to use this PERT formula. So A equals P times E to the RT power. Now, I need to write an equation for both city A and city B. Now, make a note that T is going to be years since the year 2005. So, my equation for city A, I'll let that be A. So, A is going to equal 150,000 times E to the 0.06 T power. For B started with 200,000 times E, and we have its growth rate is only 3%, so 0.03 times T power. And so we're looking, and part A says how many people are in each city by the year 2021. So the city A, I'm going to put in this number of years since 2005. So T in this case is going to be 16. So I'm going to put 16 into my A equation and into my B equation to see what they give me. Okay, so I plugged in, I get approximately these two values for the number of people in city A and city B. I rounded to the nearest whole number because it doesn't make sense to have a fraction of a person. So I just rounded to the nearest number. And now that takes us to part B. In what year did the population of city A become larger than city B? So what I'm going to do is I'm going to take my two equations. In order to do that, I need to figure out when did they equal one another. So I have to have 150,000 times E to the 0.06 T is equal to 200,000 times E to the 0.03 T. And then I want to go solve from there. Well, the problem that we have right now is that we have our variable as the exponent of both sides of this problem here, and in terms of what we want to solve for. So what I'm going to do is I'm actually going to divide first. I want to get my t's on the same side and everything else away from it. So I'm going to divide by 150,000. And I need another zero. That's going to give me E to the 0.06 T is equal to, I'm going to cancel out some of them zeros. So we got what, 20 over 15? I know I could simplify that further. Times E to the 0.03 T. And now I'm going to divide by E to the 0.03 T. So at least my T's are on the same side. Now what we have is the left side is 20 over 15. Now I have E to the 0.06 T divided by E to the 0.03 T. Remember, when you divide like basis, you subtract your exponents. So it's going to make E, so 0.06 T minus 0.03 T is 0.03 T. So divide like basis, subtract the exponents. Now I'm here. Now I solve for T. I'm going to take the natural log of both sides. So the ln of E to the 0.03 T is equal to the ln of 20 over 15. And we're going to bring our exponent out front. So 0.03 times T is it is equal to, but I want to write the ln of E, equals to the ln of 20 over 15. The ln of E is 1, so I don't technically have to write that. And then we're going to divide by 0.03. So we got the ln of 20 over 15 divided by 0.03 is going to give us our T. So this would be the number of years since our initial time frame, since 2005, and we're going to get a decimal equivalent in our calculator. All right, and we get approximately 9.8 589 years. And so what I'm going to do is I'm going to round that to the nearest year. So we get approximately 10 years since 2005. So in what year will City A become larger than City B? We're going to go with 2015. So the year 2015.